Hello and welcome back to Elementary Algebra, section 4.1 on solving systems of equations using the graphical approach. Now, we haven't had anything like this before, so we first need to understand what is the system of equation, right? So, system of equations. So in our case, for our class, it's going to be a pair of two equations whose solution is going to be either a point or line or infinitely many points. So let's take a look. Oh, sorry, or no solution. So system of equations that for us is pair of two linear equations with solution, and now we have three possibilities. Solution as one of the three, let's call cases, maybe it's better. Case one solution, also known as unique solution, x comma y. Two, many solutions, that will be a line, we'll see that. And finally, three, no solution. Now, I need to talk about the concept before we go in and just graph some lines quickly and do these problems. These problems are very structured and not a big problem, but conceptually they might create some issues. So let's see what we have. So system of equations. So I'm going to give you ax plus by equals c and dx plus ey equal f, where a, b, c, d, e, and f are some numbers. Now, what happens in this case? When you have a system like this, each one of these gives a line in a graph. So we can, because they are in this what we call a standard form, you can use the xy intercept chart to figure out the x and y intercepts, and those two lines will then graph on the xy coordinate plane. So when you get there at the coordinate plane, those two lines can arrange themselves in one of the three cases. So when you graph the two lines, for case one, they can intersect. And this point here would be that one solution, which we just read off of the graph as x comma y coordinates, which is why it's so important to draw this very precisely, because if everything is crooked, then they are going to intersect in the wrong spot, and your answer will be wrong. So making sure that this is perfectly straight and obviously done on the graph paper, because you have vertical and horizontal divisions equally spaced, is very important. They can also graph, so we can call this line 1 and line 2, all right? They can also graph one on top of the other. So this is line 1 and then line 2, which is actually the same line, right? So if I have these two to be the same line, then in that case we say infinitely many solutions. Generally we just say many solutions, but the word infinitely, it should be there. Infinitely many solutions. And as you can see, the solution is actually this line. So it's no longer intersection point, but infinitely many points along this line that goes forever to the left and to the right. And finally, the third case, when the two lines are parallel, they never intersect, which means no solution. So if you have two parallel lines like this, we say no solution in case 3. And I can say over here, because lines are parallel, so they never cross. Right? And if they don't cross, you cannot come up with a solution. So these are the three cases that you can run into when you are solving the system. You will always be given two equations, or you will have a word problem that contains two equations in terms of words. And then you can graph those two equations and find the point of intersection, which is the solution. Now, that point is a solution because it works in both lines. Clearly, over here we're going to have infinitely many solutions because every point works in both lines because one line graphed on top of the other line. And finally, the last third case, again, when lines are parallel, that means they're equally spaced forever, which means they will never intersect. And because they never intersect, we don't have a solution at all. So there will be a no solution case. Now, the lines can be given to you in standard form, which is when you use those x and y intercepts, which we studied in, I believe, 3.3. Or they can be given as y equal mx plus b. And then you do the counting method from our last class, right, from 3.5. So now let's take a look at the method here. So you will be given two equations. Let's just put, for simplicity now, negative 3x plus 2y equals to 12. And the second equation, y equals to 3. So you have your equation 1, you have your equation 2. The question is, what is the solution of the system? And in this case, you can have either one of the three. So we want to figure out if it's a one solution and then find what x and y are the solution, or if it's no solution, or if it's infinitely many. Now, when you look at this, you first analyze what type of lines you have because you need to graph, obviously. So when you look at the top, that's the standard one, which means you immediately complete the chart. The bottom one is just a horizontal line. Right? If you study 2 minutes vertical and horizontal lines, you can immediately recognize the horizontal line because whatever y is 3 is just going to go flat through y equals 3. So now we have to compute the chart, and then when we compute the chart, we will have enough information, right, to graph the line number 1. Line number 2 is a joke, right? It's just a horizontal line through 3. And as I said, wherever they intersect is going to be the place that we call a solution. All right, so to solve the top part, we have x equals 0, so that kills x. 12 divided by 2 is 6. And to solve for y-intercept, when y is 0, that kills y. 12 divided by negative 3 is negative 4. So I have my x and the y intercept, and I have the other line to be 3. So all I need to do is to draw the coordinate system and put these.
Wait, I'm confused. Where did you get 6 and where did you get negative 4?
That's calculation we learned in 3.3, where you plug in 0 and then you calculate y, and then in the second pass you plug
I didn't
in.
even. My bad. Okay,
Yep,
I got it.
good. So now we are going to graph this. So we have our x and the y coordinate system. We need y equals 6. 1, 2, 3, 4, 5. Oh, need this a little bit taller. 6. And we need x to be negative 4. So 1, 2, 3, negative 4. So now, when I connect these two lines, these 2 points with a line, we get our line 1. Line 2, as I said, is easy because it's just a horizontal line through 3. And hopefully, if you did this carefully enough, you will see that line 1 and line 2 intersect perfectly here at negative 2, 3. So we say that the solution is negative 2, 3. And you can check this. You check by plugging in these numbers into the problem, and if the values work out to be correct, right, then the solution is correct and we move on. So the solution happens wherever you have your intersection of the two lines. We have line 1 and line 2. So to check, and again, don't lose points. If the problem says solve and check, make sure you do the check procedure because it brings points, right? Last time, a lot of points lost across the board because you guys didn't do the check procedure at all. So what do we have? We have negative 3 times negative 2 plus 2 times 3 needs to be 12. So we are using the equation. We plug in our x and y, and we just want to make sure that it's a true statement when we compute. Well, negative times negative is a positive, and 6 plus 6 is 12. So that's good. We know that this problem is good because we took the solution, plugged it back into both equations. Now the second equation, y equals 3, and we can see that y is 3. So there is, right, nothing to check in the second equation. But the first equation was a calculation, and we were able to come up with 12 equals 12, which means that this problem, because the point works in both of equations, that means this problem is solved correctly. Now, I don't like teaching mathematical concepts without giving you a hint of where this is useful if you are a person who wants to use mathematics to make life easier and better. So there is a very simple problem which we work on in either algebra courses or pre-calculus courses, and the problem is a little bit old. it talks about the amount of text messages, because the problem is old from the era where people used to pay per text message sent. So if you send your friend a text message, you get billed 10 cents, whatever. And it used to be very expensive to send text messages in the past. But then there is always something that you pay with cell phones. So this problem can be updated easily to buying data plans today. You know how many gigabytes of data you're going to use every month. So we can update and change the problem. But the idea of these problems is to introduce the fact that if you are comparing two plans which have monthly payment plus the overcharge payment, you can pick the better plan knowing your use for either, as I said in the past, was calling, then text messaging, now it's data plans. So people used to pay, believe it or not, per minute of talk. People used to pay per text message. And today people pay data plans. So it says unlimited calling and unlimited texting, but you have to pay data plans, which is obviously they know they're going to do well on data plans because you guys waste a lot of time on social media. So what happens now is you can have those two plans and they will intersect somewhere. And that point, that solution point, is when the two plans cost the same. So you would say that, you know, I don't know if it's like 4 gigabyte of data, let's say, is the intersection point. So up to 4 gigabyte, one plan is better, as you can see. Because see, this bottom line is line 1, and the top line over here is line 2, but they switch later on. And they switch when they go through the solution point, they switch. So if this is your money and this is your gigabytes of data used, you can see that the plan 1 is better because you pay less money because the line is lower. You pay less money for plan 1, but then if you go over 4 gigabyte, that plan will be more expensive. And the plan 2 is more expensive if you're going to use less than 4 gigabyte, but it's more expensive than when you use it later. So these are the things that you guys can apply to many areas of your life if you again care about managing money, saving money, and all of these things, because you know it can be computed, which is why rich people always get richer. They can do these kinds of calculations, and they know exactly what deals are good and what deals are garbage. Another aspect of this would be choosing medical insurance, for instance, when you work for a company and they offer two plans. One plan has higher copay, the other one has lower copay, but the amount of percentage that you use is flipped, right? So now you go and you say, all right, so if I'm going to go to a doctor this many times a month, right? Which plan is better? So there are different plans out there because people have different conditions. Some people are perfectly healthy and the other ones are not, right? So the people that are perfectly healthy clearly, right, are not going to the doctor very often. They're not going to spend $15 on copay or whatever every time they go in. And because of that, if they're going to go to doctor once or twice a year, high copay and low premium is perfect. The other people who go to the doctor all the time because of, let's say, a chronic issue or something, and let's say they have to go to the doctor every week, well, that means a lot of copays. So the plan should be the one that has lower copay, right? Because you do not want to pay high copay going in every week. So these are the things that, decisions in life that when you recognize the mathematical concept, you can use to immediately make life much better in terms of saving money and making good financial decisions, not just, let's try this and then if it doesn't work next year, we'll switch. Well, you already lost this money, right, in this year. So that's never a good strategy to kind of eyeball it and say, okay, this looks good because, as usual, it goes in the economy. The deals always look good, but at the end, it's the other side that usually profits more than the one who is looking into a deal. So um, when you look at this, and I did with the cell phones and data plans, or texting or whatever from before, well, you can upgrade that to your insurance. You can upgrade that health insurance, life insurance, and a whole bunch of other areas. It can be transferred into the business and so on. We are solving a lot of these um, curves. There is also a very good in economics. There is a very good called supply and demand curve, um, which some of you who study business will eventually learn. And it is a very good graphical representation. Again, it's going to look something like this, right? What we did, where you can take a look at what would be the good price to set for the product that you want. Um, the best example that I have in the past was, if you guys are familiar with the Wii console, right when it came out, it was on back order for 6 months. They couldn't make enough units because people were buying it like crazy, and it was only like something like $250, I think it was, which was almost half a price as the Sony PlayStation and so on. But it had this component that you can interact with the screen, and a lot of people really wanted that, so they were taken by surprise. They could have charged double or triple the price and still sell out all of the units they made, but again, they didn't do the good analysis, right? So they lost probably a lot of money, and a lot of people bought the thing at the cheaper price. um, it's a lot of this kind of analysis that goes into the business. So let's first learn again. Let's learn the basics, and then later on you can try and use it for your own benefit in the situation. Like you have some kind of situation where this could potentially save you some money. Let's take a look at a couple of examples, and hopefully some of them will have infinitely many solutions. Some of them will have no solution because they're parallel and so on. So let's see. I'm just going to pull random ones from the homework from the textbook, and then you guys go on and solve these problems at home as well. So let's see. I want to find a problem that will have um, one of the y equal mx plus b graphs, but I don't see them readily available. Just give me an hour, I'll be right with you. Wow, really? None of the problems on any of the pages? That's terrible. Whatever, I'm going to make it up. Let's go. So let's say you have 2x plus y equals to 3, and y equals um, y equals 3x minus 2. So here's your line 1, here's your line 2. The goal is to graph both of these lines on the same coordinate system and then see where they intersect. So the first one is again the XY intercept chart, and the second one is basic counting, which was what we did last class. So we first solve the chart. So when x is equal to 0, that kills x, and then y is 3. And then when y is equal to 0, we get 3/2. 3/2 is 1.5. So you can use it as a decimal if it's easier for you to graph it. So 1.5 is exactly in between, in the middle of 1 and 2. And the second graph is just counting, so we don't have to worry about we don't have to worry about that one. Let's graph this. Why are you red? Can I select it now? Yeah, I give up. That's too long. Maybe I can move it. All right, so here is our coordinate system, and what I need to do now is I need to get the x and y axis labeled, and now let's go graph line number 1. So we need y to be 3. So 1, 2, 3. And x to be 1.5. So this is 1, this is 2, 1.5 is in the middle. And then we connect those 2 points with a straight line. There we go. And then we have the second line, which says go to -2 on y. So this is our line 1. Go to -2, and then you have your slope rise over run, which is what we covered last class, is 3 up, 1 over. So we count 3 up, 1, 2, 3 up, and then 1 over. And as you can see, that one landed immediately on the second line. So now, when you look at this line number 2 over here, you see that they intersect at 1, 1, which is the solution. So when you draw these carefully and straight and all of that, you guys are going to have the solution intersect at 1, 1. Now we check that. We plug in 1 plus 1.
Could you where did you get the rise over run again with the 3x -2?
That's a slope.
Yes. So you did. What did you do? I just like missed that.
So in the last lecture, last class, we said y equal mx plus b
Yes.
is the form, and m is our slope. So in our case, m is equal to 3. But you need a fraction there because you need to go rise over run. And number
Okay.
3 is a fraction because you can just put over 1. And now you have rise over run, 3 up, 1 over.
Okay. All right. That makes sense.
Good. And so now we check the first equation when we plug in 1 and 1. And we got a correct mathematical statement. Now we check in the second equation. Is 1 equal to 3 times 1 minus 2? 1 equals to 3 minus 2. 1 equals 1. So that's correct as well. And what we have here is definitely a solution because we checked in both equations, and in both equations it gave us the correct statement. If you plug this into one or both of the equations and you get a wrong statement at the end, then the solution is definitely not good. So you have to make sure that you check your answer so you know, right? You can walk away from the problem knowing it's correct rather than hoping that it is correct. Plus, when you're choosing insurance in life, when you're choosing data plans and streaming services and all of these kind of things, there's no one to check your work. So you are either getting ripped off because you just don't know any of these things. So you are just, going like what looks the best. Or you figured out how these things are done in the math class, and then you are applying those concepts to pick the best plan and the best, everything for you and your family. So everything in life has the price. That's the way the world works. So if you have the knowledge of how to do these things, then that's it. Great. Let's take a look at another problem. Say you have 3x minus 2y is equal to 6, and negative 6x plus 4y is equal to, I don't know, we can go with 8, whatever. So we are still looking for the solution in this case, and we know exactly what we need to do. Now we have two standard forms, so you are supposed to solve the x and y intercept chart because that's the standard form. This one is also standard form, so yet another x and y intercept chart. So I'm going to let you guys fill these values in. So I'm going to give you a few minutes, and then when you're done, we're going to graph this and see what the solution is. Can anyone tell me the numbers for the top?
0, -3.
Okay.
Right? And 2, 0. Right?
2, 0. Yes. Okay. Do you guys have it for the other one?
I got 0 and 2, and then negative 0.75 and 0.
Negative 0.75. That's negative 3/4. Yeah. Negative 3/4. So when y is equal to 0, then you get 8. Yeah, negative 8/6. Oh, I think you have it backwards. Or do I have it backwards?
Yeah, I got -4/3.
Yeah, negative 4/3. Negative 4/3. There we go. Okay. So now we are going to do the let's see. Well, we can just do the graph and see what we can come up.
Do you think it's easier to plot it on the graph if you put it into an improper fraction?
Whatever makes you happy. 1 and 1/3. So yes, it's gonna be the number tells you how many whole units, and then 1/3 of the remaining space. So the answer is yes, but then everyone is different. So I'm not going to mandate one way or the other. Whatever you guys, whatever makes you happy. This is your happiness is our primary concern. All right. So first line is -3 and +2. And that's our line 1. Line 2 is y equals to 2, and then a -1 and 1/3. So -4/3 is -1 and 1/3. So that means between -1 and -2, you split this into 3 even parts, and then you draw the line. Ooh, they look parallel to me. So let's just verify that they are parallel, because if they are parallel, that means no solution to our system. And the way to verify that is we know from last class, again, that two parallel lines have the same slope. So if I solve these lines and transform them into, solve them for y, then we transform them into y equal mx plus b, in which case you can just read off the slope. So when you transform 3x minus 2y equal to 6, you take away 3x. This is one of those sections from chapter 2 when you were flipping formulas around. This is the reason why you learn it, right? So we have -2y equals -3x plus 6. Divide everywhere by -2, and you have y equals 3/2 x minus 3. So we used that, I believe it was like 2.4, I think, formulas where you solve for y, and when you solve for y, you actually get your y equal mx plus b. So here's the m, 3/2. So that was the first equation. Now we're going to take the second equation and do the same thing. So we have negative 6x plus 4y equals to 8. Add 6x both sides. We get 4y equals 6x plus 8. Divide everywhere by 4. And you get y equals 6 and 4 cancels down to 3/2 x plus 2. Look at that. Awesome. Same slope means parallel lines. Parallel lines means no solution because parallel lines never intersect, and because they don't intersect, there's no point of intersection to be our solution. So we have what we what we have. All right. Let's take a look at another problem from homework. So let's do 2 more examples, and that should be good enough, I think, I hope. There's nothing else to learn here. Systems of 2 equations with 2 unknowns. X and y are both unknown. And when you graph the 2 lines, you will have the either intersection or no intersection, and you have something. So let's see what we have here. 2x minus 4y equals to 8. So 2x minus 4y equals 8. And y equals negative 1/2 x minus 4. All right, so I'm going to ask you to graph this completely on your own, to figure out which method you have to use, and then whether you have a solution or no solution or infinitely many solutions, or something has to happen. Anyone done yet? How many solutions? Hello? It should be quick. I mean, this graphing is not really asking you to compute much at all. I guess you haven't practiced yet chapter 3, so you're slow with this stuff. But this should be done in maybe 2 minutes top. All you need to do, you come up with your x and y 0, 0 because it's a standard form. When x is 0, we divide by -4, we get -2. When y is 0, we divide by 2, which gives us a 4. The bottom form is already in accounting, so we don't have to do any work there for calculations. And all I need to do is to graph everything and done. So we have x is 4, so we have 1, really? 1, 2, 3, 4 on x, and then -2 on y, and we connect. So that's our first line. And the second line, we start at -4, and we go 1 unit down, 2 units over. We just count. Oh wait, my -4. I missed. Negative, because I put -2 too low. -3, -4, 1 unit down, 2 units over because of the half. And now, but usually these problems work out nicely. There we go. And they intersect here at -2, -3. And I can quickly check if that makes sense by plugging in -2, -3 in each of the equations and work it out. So now to check it, 2 times -2 minus 4 times -3 should be 8. So that's -4 plus 12. -4 times -3 is positive 12. And yeah, 12 minus 4 is 8. 8 equals 8. Yay! The second equation should be -3 is equal to -1/2 times -2 minus 4. So -3 equals to, this will just become 1 because you have a half of 2. Negative times negative is positive, and then you just have half of 2. Well, half of 2 is 1. Minus 4, and there you go. -3 equals -3. So we know that this is a good solution because it worked in both equations. Now, without the check procedure, as I said, it should take at most
I told her I can't
2
talk,
minutes.
Mom.
Right? So the most it can, it should take is 2 minutes to solve this. Let's see another one, and then we'll take a break. When we come back, 4.2, we will be solving the same equations, but we will be using calculations and algebra rather than dealing with this. Okay, so let's go with uh, 3x plus y equals to, 3x plus 2y equals to 6. and y is equal to negative 3/2 x plus 2. So let's see what we get, right, when this is the system. So we have equation 1, equation 2. Again, we're supposed to graph this on the same coordinate plane and see what we get. Any solutions?
Is it a no solution?
I don't think so. Oh, it is a no solution. I needed to make this into a 3. Ah. Yeah. I wanted to have that one line because we haven't had that problem yet. So I was aiming for the solution to be infinitely many solutions or one line, because one line has infinitely many points. Yeah, such is life. Let's see. So the top equation is a standard form, which means we can do our 0, 0 thingy. Plug in 0 kills x. 6 divided by 2 is 3. And then plug in 0 for y, kills the y. 6 divided by 3 is 2. So we have our points, and then the second one over here is just a basic y equal mx plus b, which we can quickly graph. So let's see. I go and put y equals 3 and x equals to 2, and we connect these two using the straight line. And then when you take a look at the second equation, you see that you have the y-intercept of 3. So let's graph the second equation red. We graph here 3, and then we have to go 3 units down, right? Remember, rise over run. So rise of -3 is 3 units down. So we go 1, 2, 3, and then you go 2 over, and you get the same point. So the red line and the black line graph at the same spot. So since they're same line, that means many solutions, infinitely many solutions, because there are infinitely many points and they all agree, they all match, right? Any point from the red line has the corresponding point at the same location from the black line. So both of these lines will have infinitely many points that match, and that's why there are infinitely many solutions. That means that any point you pick from this line will work in both equations. And you can test that with 2, 0, for instance. It will work in both equations, or 0, 3. Those are the easy ones. But then you can also pick, I don't know, this point here. That point looks nicely lined up as 4, -3. So if you put 4, -3 in both of these, it will work. And the reason why so many points work is because there are infinitely many solutions, but they all have to be on this line. You cannot put a point right there and try that point, because that one would not work, because it's not on the line. But any point you pick from the line, when you have this situation, would give you correct answer. So you have the situation when you have one solution, when the line intersects at one point. Situation when the lines are the same line, it graphs one over the other, in which case you have infinitely many solutions. And finally, when the lines are parallel, then there is no solution, because the lines will never intersect to create a solution. And that is it. That's the graphical way to solve, graphical approach, right, to solve systems of equations. I did talk about application. We will obviously review those. I did tell you that you can use this to pick a good deal on health insurance and cell phone plans. And even if you're renting the car between different companies, because they all give you the information on how much you pay flat per day and how much you are paying per mile. So if you have that information, you can figure out which deal is better if you know how far you're going to go. Usually people rent the car to, let's say drive to DC and back, so you are not, putting mileage on your car, depreciating the value. You're not, using up your tires. You are not using up your brakes, oil change. Like all of that stuff is factored in if you, let's say, want to go to DC and back for like a weekend or something, right? So renting a car kind of makes sense, right? You don't have to worry about, if the car is stolen, then there is the insurance that goes through the rental company, right? You don't have to deal with, looking for your car and all that kind of stuff. So, a lot of people will rent a car for something like that, to drive somewhere out of the comfort zone, and comfort zone being, you know, work and grocery shopping and stuff like that. So you can use that to, you can use this knowledge to compare different locations, like different prices, and then pick which location has the better price. Now we'll see some of the word problems when we finish chapter 4.2, section 4.2. So we'll deal with this stuff then. So let's take a short break. When we come back, we are going to talk about these problems again, but this time we are not going to graph them. We are going to solve them by what we call method of substitution.